Harvard professor Clayton Christensen developed the theory of disruptive innovation in 1995. Disruptive innovation is the introduction of a product or service into an established industry that performs better and generally at a lower cost than existing offerings, thereby displacing the market leaders and transforming the industry. The term disruptive innovation is very often misconstrued. Originally, the theory was simply a statement about correlation. In an interview with the Harvard Business Review, Christensen said, "I never thought that the word disruption had so many connotations in the English language that people would then flexibly take an idea, twist it, and use it to justify whatever they wanted to do in the first place." He even showed concern about the widespread use of his theory. Today's society basically lives off of disruptive innovations, which include but are not limited to smartphones, video games, laptops, drones, and hoverboards. This is a graph provided by my University of Arizona professor, which shows 6 distinct categories of disruptive technology. You can see here that these include enablers, catalysts, morphers, enhancers, superseders, and breakthroughs. Based on this and much other research, I came to the conclusion that antibiotics are the most important disruptive innovation. Not only did antibiotics enhance the medical field tenfold, but they are one of the greatest breakthroughs of all time. I know we all enjoy spending countless hours watching mindless videos on TikTok, but I'm sure we would all prefer the technology to save mom when she got an infection. The names most commonly associated in the history of antibiotics are Paul Ehrlich and Alexander Fleming. Ehrlich was a German medical scientist known for his pioneering work in hematology, immunology, and chemotherapy, and for the discovery of an effective treatment for syphilis. Alexander Fleming was a Scottish bacteriologist and military physician who in 1928 inadvertently discovered penicillin. Ehrlich had an idea of a magic bullet that selectively targets only disease-causing microbes and not the host. This was based on observation that certain dyes could stain specific microbes but not the others. His argument was that chemical compounds could be synthesized that exert their full attention on the parasite harbored within the organism. This led to a large systematic screening program to find a cure for syphilis. Eventually, 2 drugs, salvarsan and neosalvarsan, both used in the treatment of syphilis, became the most frequently prescribed drugs until it was replaced by penicillin in the 1940s. Paul Emmerich's systematic screening approach became the cornerstone of drug research strategies in the pharmaceutical industry, resulting in the creation of thousands of helpful drugs. Some of you might be familiar with the serendipitous event on September 3, 1928, in which Alexander Fleming did not properly clean his lab and some mold got into one of his petri dishes. This led to his discovery that certain molds kill bacteria, and he developed the miracle drug penicillin. For 12 years, Fleming rigorously tried to get other scientists interested in his discovery, and even nearly abandoned his work in 1940. But luckily that same year, a team from Oxford came forward with its work, stating that penicillin was ready for clinical research. 5 years later, in 1945, Alexander Fleming received the Nobel Prize in Physiology, along with 2 of his colleagues, Howard Florey and Ernst Chain. This image shows how penicillin is produced by scientists. Once penicillin and other antimicrobials, such as salvarsan and prontacil, proved to be exemplary, their research set up paradigms for future drug research, which led to the discovery of many new antibiotics. Here you can see a timeline of antibiotics from the years 1900 to 2010. One of the major threats faced by antibiotics were antibiotic resistances. This is the ability of the bacteria to resist the effect of the antibiotic they were originally sensitive to. This still poses a threat today. The CDC, the Center for Disease Control, says at least 2 million become infected with antibiotic-resistant bacteria, and more than 23,000 people die annually of these infections. Prior to the beginning of the 20th century, infectious diseases accounted for high mortalities worldwide. Diseases such as cholera, smallpox, pneumonia, syphilis, typhus, and plague killed thousands. The average life expectancy was only 47. The eventual discovery of penicillin would mark the beginning of the antibiotic era. The 1950s to the 1970s were named the golden age of antibiotics. The new approach to discovering new drugs became the modification of existing drugs. The life expectancy soon raised to 78 years, thanks to these highly disruptive innovations.